Okay, let's start. Good afternoon, everybody. I hope you're able to hear me. If not, please indicate so in the chat box.
Yes, sir, you are
Anyway,
audible.
so we have this prime number P, right? And we have a P field K. Now, as I explained last time, a P field is just the field of fractions of a certain kind of ring O. And what kind of ring is O required to be? It's of course integral, but it's also local. Local means that it has a unique maximal ideal. And this unique maximal ideal is actually principal. Okay. And finally, this ring O is complete for this maximal ideal P. So complete in the sense that it is the inverse of O modulo P to the n over all n. Right? So this is the kind of ring that we are starting with. K is the field of fractions of that ring.
Hello.
We call such a K a P field. And that prime number P is to be distinguished from this P, which stands for the unique maximal ideal of our ring O, right? Then we have little k, of course, to be distinguished from capital K. This little k is just O modulo P, and it's called the residue field of the ring O or of the field K, right? And so there seems to be a problem.
Hello. Hello. Hello.
So we cannot see.
Just a moment. I'll get back to you in a moment.
Hello.
So I have to share this one now. So I'm sorry, there seems to be some, okay, it is connected or, yeah, it's connected. Just wait a moment, huh? Okay, I hope you are able to see it again now. There's a small Wi-Fi problem. So this little k is the residue field of the ring O of the P field capital K. And it's being called a P field because this little k is a field of characteristic P. And I'll denote by little f the degree of k over fp. And by q, the cardinality of this field, little k. So that's the notation. As we have said, there are two main examples. K could be QP, or it could be K power series T. So these are just examples. And today, what we are going to prove today, we are going to prove that if K is a P field, implies that either K is a finite extension of QP, so either K over QP is finite, or K, this capital K is little k power series T. So here, this example, and this example can be found here, and this is enlarged a little bit in the sense that, oh goodness, this is bad. I'm sorry. I'll now probably just work with this thing here. So I'll stop that thing, and I have to start doing this. Just a moment, huh? Okay, so here's the share screen thing. Yeah. Okay, so I'm sorry that I can't point out things here, but let's manage, let's try to do as much as we can. Okay, so we have this notation. We have a P field capital K. O is the ring of integers of that P field. P is the unique maximal ideal. Little k is the residue field. F is the degree of that residue field over Fp. And Q is the cardinality of the residue field. And today, one of the things we are going to do today is to prove a structure theorem. So what we have just now defined is something abstract. It has been defined by a system of properties. And the structure theorem will tell us that these are the only possibilities for a K field, for a P field, excuse me. So we will prove that a P field, if it has characteristic 0, then it is a finite extension of QP. And if it has characteristic different from 0, then it is actually little k power series T, isomorphic to this field. Okay, so let's get going. One of the things that we did last time was to define this subset R, which is just the set of roots of the polynomial t to the power q minus t, right? It's a polynomial of degree q. It can have at most q roots, but we saw that it has exactly q roots. So this set R has q elements, and moreover, the reduction map from R to little k is a bijection. And it's actually R is closed under multiplication. Although it's not closed, it may not be closed under addition. It is always closed under multiplication, and the reduction map respects that multiplication. So that's what we proved last time. Okay, so let's also choose a uniformizer pi of k, which always, of course, means that pi is a generator of this maximal ideal P, which by hypothesis is a principal ideal. Okay, now we have the reduction map not just from R to little k, but for every n, this R to the power 0, n, this is just the set of all sequences A0 up to an minus 1, where these AIs are in the ring, are in the set R. And this reduction map sigma n bar, it takes such a sequence to A0 plus A1 pi. Pi is this uniformizer which we have chosen. If you fix a uniformizer, then you get this map sigma n bar. For each choice of pi, there's a map. If you choose a different pi, you'll get a different map. But the fact that it's a bijection, which is what I'm going to prove next, is of course independent of the choice of the uniformizer. Anyway, so we have chosen a uniformizer and we sent such a sequence A0 up to AN minus 1 to the reduction. This overline is the reduction of an integer. Integer is an element of the ring O to the field K. Oh, well, in this case, it's not, excuse me, I mean, this is very funny, but in this case, the reduction is not from O to the residue field, but from O to O modulo P to the N. Okay, so to the sequence A0 up to AN minus 1, I associate first of all the integer A0 plus A1 pi and so on up to AN minus 1 pi to the N minus 1. It's an element of O. Then I put this bar to indicate that I take its image modulo P to the N. So that defines the map sigma n bar. And the claim is that this map is a bijection for every n. Okay, nothing is being said about this being a homomorphism. In fact, asking whether it's a homomorphism or not makes no sense because we have not given this set R any ring structure. The thing on the right is a ring. The thing on the left is at most a multiplicative monoid. Okay, but forget about the monoid structure. Let's just look at R as a set. Then you have these sequences of elements of that set, and such a sequence is sent to this element of O modulo P to the N. The claim is that it's a bijection for every n. I think this we proved this last time. So it followed from this the fact that these are bijections and that these are compatible when I replace n by n plus 1. When I replace n by n plus 1, first of all, I have a map on the left from n plus 1 to n. I have a map from on the right from n plus 1 to n, right? Which means O modulo P to the n plus 1 to O modulo P to the n. That, of course, is a homomorphism of rings. The one on the left is just a morphism of sets. So I have the bijection sigma n plus 1 bar and the bijection sigma n bar, and therefore I get a square, and that square is obviously commutative. It doesn't even require any thought. So because of these commutative squares, in the limit, I get a bijection from R to the n. This n is the set of natural numbers. So R to the n is the set of all sequences A0, A1, A2, and so on, where these AI are elements of the set R. And sigma is the inverse limit of these sigma n bars. It maps R to the n into the ring O. And it's a bijection. That's what we proved last time. So the notation for this, the image of this sequence A0, A1 up to, or all the way up to infinity, the image, this sigma of this sequence is denoted by this notation here on the right. This is sigma I in sum over I in n of AI pi to the I. Okay, so this is a very reasonable notation for this this element. So let's just take a small example. If my ring O were the ring ZP, then what is this subset R? It's going to be omega of FP, right? It's omega of K in general, where K is the residue field. In the case of ZP, the residue field is FP. So R is omega of FP. Omega, remember, is the Teichmüller representative. And we can choose the uniformizer to be P. You can also choose it to be minus P. Nobody stops you from doing it. It's entirely up to you. Okay. So, okay. So what is, so here in blue, I have this remark which says that if A is an element of, is an integer from 0 to P minus 1, this P minus 1 should be included. Here, it should be a closed parenthesis. 0 to P open bracket is what was meant. So it's 0 to 0, between 0 and P minus 1 inclusively. Then A need not be equal to omega of A bar. A bar is the reduction of A modulo the ideal P. So A bar is an element of K or FP in this case. So I can talk of its omega. I don't get back A as omega of A bar in general. But for A equal, for example, for A equal to P minus 1, we have omega of A bar is going to be minus 1. And minus 1 is, of course, not the same as P minus 1 at all, right? So this is just to say that earlier, we had written every element of the ZP uniquely as a power series in P, and the coefficients were these integers from between 0 and P minus 1, inclusive, right? Now, so these could be thought of as the digits, 0, 1, up to P minus 1. They are sort of the digits in this base P or p-adic expansion is what this power series, such a thing is going to be called, pi-adic in this case. Anyway, so if you apply that result to this case ZP, then what follows is that every X in ZP can be written uniquely. For every X, there's a unique sequence A0, A1 in FP, such that X is sigma that map from R to the N to O, sigma of omega AI. Or in other words, it's the sum over I in N of omega AI, P to the I. Okay. So here is an interesting exercise. You might try your hand at it. So if you know the p-adic expansion, so this is what should it be called? It's not the p-adic expansion, because in the p-adic expansion, the digits are supposed to be the integers 0 to P minus 1 inclusively. But so whatever, if you know this, the sequence corresponding to X and the sequence B0, B1 corresponding to Y, you try to find out what the sequence for X plus Y and XY are going to be. Okay. So let's start today's lecture. The first thing I want to prove today is that if my P field K happens to have characteristic P, you know, this P is the characteristic of the residue field little k. But if the P field K itself happens to have characteristic P, then there are these things which follow. Okay, what are the assertions? First of all, R is a subfield of K. I had only proved that in general, R is just a submonoid of the multiplicative monoid. In other words, it contains 1 and the product of any two elements that it actually contains. But if the characteristic of the field capital K is equal to P, then R is actually a subfield. And the reduction map, which was just a bijection, or in fact, just a morphism of multiplicative monoids in general, is actually an isomorphism of fields. Okay? And the third assertion is that for every uniformizer pi of K, I can define this composite map. Now that R is a field, I can define R power series T, which is just a ring. I mean, which is a ring, right? This ring is in bijection with R to the power n, because the ring, I mean, after all, this power series ring, what information does an element of this ring contain? It is just a sequence of elements of the field R, a sequence A0, A1, A2, and so on. So this map is completely obvious. This power series being sent to the sequence of coefficients. And then I have this map, sigma, which I've defined in general, which sends this such a sequence to this summation where, I mean, this is pi, the uniformizer pi is fixed, right? And the claim is that this map from RT, R power series T, to O, now it's a map of rings, it's a bijection of rings. And the claim is that it's an isomorphism of rings. So, and this isomorphism, of course, takes the uniformizer T, or the indeterminate T, to the uniformizer pi of the ring O. That's obvious because T here as an element of this power series ring is 0 plus 1 times T plus 0 times T squared, etc., etc. So this will go to the sequence 0, 1, 0, 0, 0, etc. And that will go to the summation. So it's going to be 0 plus 1 times pi plus 0 times pi squared, etc. Obviously, so that's equal to pi, right? Okay, so let's prove this. Now, first of all, R is a subfield. We already know that R is stable under multiplication and 1 is in R. In other words, R is a submonoid of the multiplicative monoid K. Okay, a field or a ring is an additive group plus a multiplicative monoid, and these two structures have to be compatible in the sense that, what is it? Something is distributed. Maybe it's the addition which is it's multiplication which is distributed over addition. I don't remember the terminology, but the idea is that this field K is there's the additive group, but there's also the multiplicative monoid structure as well. So R is a submonoid of the multiplicative monoid. So what we need to show is that it's a subgroup of the additive group. And in order to show that it's a subgroup, you have to show that if two elements belong to it, then their sum also belongs to it. Maybe you want to show that it's 0 belongs to it, but 0 belongs to R is clear because, right? I mean, it's part of the, that's how R works. It's easy to see that 0 is actually equal to omega 0. So 0 is in R. Okay, so if x and y are in R, then x to the q is equal to x, because R is the set of roots of the polynomial t to the q minus t. So x to the q is equal to x and y to the q is equal to y. What is x plus y to the q? Q is a power of p, and we are in characteristic p. That's the hypothesis. That's the hypothesis, right? If the characteristic of k is equal to p. So we are in characteristic p, Therefore, this x plus y to the power q is going to be x to the q plus y to the q. And x to the q is equal to q, and y to the q is equal to x to the q is equal to x, and y to the q is equal to y. So x plus y to the power q is x plus y. In other words, x plus y is also a root of the polynomial t to the q minus t. So x plus y is an R, and therefore it's a subfield of the ring O. Fine, we have proved that it's a subfield. Now we have to show that the reduction map is an isomorphism. Oh, well, that's easy, perhaps, because we already know that it's a bijection. It's a bijection, and it's a homomorphism. That's a property of the reduction map, right? It takes sums to sums and products to products, and one to one, if you wish. So, and any bijective homomorphism of rings or fields, I mean, in this case, fields, is actually an isomorphism, right? Okay, let's come to the final thing, which shows that the composite from R power series T to O, this rho is an isomorphism of rings. Okay, so first of all, I want to show that it's a bijection. So why is it a bijection? That's because you know, this rho, of which I want to prove that it's an isomorphism, can be viewed as the inverse limit of certain maps from RT modulo T to the N to O modulo P to the N. So these are the maps A naught plus so on up to an minus 1 T to the N minus 1 bar. The bar here is reduction modulo T to the N, going to the corresponding element in O modulo P to the N, where this T is replaced by pi. Okay, so in this case, these are this is a bijection, so is this, and the composite is a homomorphism. It's clearly visible that it's a homomorphism, and a bijective homomorphism is an isomorphism. Okay, so this was not very difficult. Now, so the upshot of what we have done till now is that if I have a K field, I keep on saying K field, I want to say P field. If I have a P field K, and if that K has characteristic P, then it's actually isomorphic to R power series T, where R is a set of Teichmüller representatives of the residue field K. You know, you can just think of R as being a copy of K sitting inside capital K. R is a canonical way of injecting little k into capital K as a subfield. Okay, and the whole field capital K turns out to be just the K round parses, K double parenthesis T, not K, R double parenthesis T, right? Okay, so K and little R and little k are actually essentially the same. Okay, so now let's look at what happens if the characteristic is different from P. So the first claim is, if the characteristic is different from P, then it has to be equal to 0, meaning it cannot be equal to some prime other than, it cannot be equal to some prime other than P. So what we have to show is that if the characteristic of K happens to be some prime, then that prime is equal to P, which will be a contradiction because we are starting with a field, P field K, which is of characteristic different from P. So the only possibility is that the characteristic of K is 0. After we have proved this contradiction. Okay, so let's start with the assumption. Let's make this assumption that the characteristic of K is some prime L. Then L times 1 is going to be equal to 0 in the ring O, because that's what it means for capital K to have characteristic little l. So L times 1 is going to be 0 in the residue field as well. Now if L times, actually I didn't even need to go to the residue field. I didn't even need to go to the residue field. I could have just said it here. I mean, if L some prime times 1 is equal to 0 in a field, then that prime has to be the characteristic of that field, right? But yeah, okay. Yeah, okay. Yeah, so it could be the characteristic of capital K. But because we don't know the characteristic of capital K, we are trying to determine it. But we do know the characteristic of little k. It is P by definition. Yes, so we couldn't have worked in capital K. We have to reduce and work in little k. So L will turn out to be equal to the characteristic of little k, which is P by definition. So L will have to be equal to P. And that's a contradiction because we are taking a field of characteristic different from P. So the only way out is for K to have characteristic 0. Okay, so I want to define this notion of the absolute ramification index of K. Yeah, before that, are there any questions? I'll stop for a few minutes and see if people have questions, right? Okay, so there's somebody in the chat asked whether this ring O is going to be a discrete valuation ring. And the answer is yes. It's one of the things which you can prove easily from the fact that the maximal ideal P is principal.
Yeah, valuation.
And you can actually show that every ideal of this ring is a power of the maximal ideal, and therefore every ideal is principal in particular. Okay. So I come to this notion of the absolute ramification index of this K. K is a P field. Now, if the characteristic of K is equal to P, then I just define the absolute ramification index to be plus infinity. Okay? This is not very enlightening, but you'll see that that's a reasonable thing to do. The important thing is that if the characteristic of K is equal to 0, in which case, of course, P is going to be different from 0 in the ring O, right? Because if P is equal to 0, the characteristic of K would be P and not 0, as the assumption is. But P, although it's not 0 in the ring O, it's equal to 0 in the residue field, little k. So this P, the number P, will belong to the ideal P. Okay, and as such, you will be able to write this P as some power of the uniformizer times U. So here I'm already using the fact that the only ideals of this ring O are the ideal P, its square, its cube, its fourth power, and so on, right? So this integer P, the number P, will belong to some power of the prime ideal, the eth power of the prime ideal, but not to the next one. For some E, there's going to be a unique E such that P belongs to P to the E, but not to P to the E plus 1. There has to be the existence of little e follows from the fact that this P is different from 0. It cannot belong to all powers of the prime ideal P, because the intersection of all powers of this ideal P is actually 0. Okay. So we continue with the assumption that the characteristic of K is equal to 0. The first claim is that this O, the ring O, is actually a ZP module. Okay. Now, how is that? Or in fact, I want to say that it's a ZP algebra is a better way of saying it, meaning it's a ring already, and it contains a ZP is basically what is being said. So why does it contain ZP? So look at the ideal, not prime, the ideal generated by the number P in the ring O. It's by definition the eth power, by the definition of E, is the eth power of the maximal ideal P. So the ideal generated by P to the n is going to be the n times eth power of the maximal ideal. So Z is contained in O, that's because the characteristic of K is 0. So we'll get these inclusions of Z modulo P to the n Z in O modulo P to the n E. So that's going to be an inclusion of rings for every n. And what happens if I have n plus 1 and n? Then there's this map from n plus 1 to n on the left, from n plus 1 to n on the right. And of course, I have these inclusions, the horizontal inclusions. And this diagram, of course, commutes. Because, I mean, this is more or less by definition. There's absolutely nothing to check or verify here. So what you get is an inclusion in the inverse limit or the projective limit. You get an inclusion of ZP, inclusion of rings. So this O becomes a ZP algebra. Now, the next claim is that as a ZP module, this O is actually free of rank E times F. So I've defined this E as the absolute ramification index of the P field K, which meant that it is the power of, here's in green is a definition of E. The number P belongs to the eth power of the maximal ideal, but not to the next one. Not to the next one, which is smaller, of course. Okay, so here that was the E. And what was this F? F is, of course, the degree of little k over Fp. That's how F was defined. Little k is the finite extension of Fp, because capital K is a P field. So little k contains fp, and it's a finite extension, and f is the degree. So in order to prove this proposition, I claim first that the dimension as an fp vector space of O modulo p times O is EF. The dimension of, as an fp vector space of O modulo the ideal p, not the ideal generated by this number p, but this ideal p, the curly p, that of course is equal to f, because that this quotient here, in the case of the ideal p here, would be the residue field k. But when I replace the ideal p by the ideal generated by the number p, then the dimension is equal to EF. So this p times O is of course p to the E. That's what we have, that's more or less the definition of this E. Now this has a filtration. You have O modulo p to the E, but that contains p modulo p to the E, which contains p squared modulo p to the E, and so on, all the way up to p to the E modulo p to the E. This p to the E of modulo p to the E is of course equal to 0. And the quotient, what is the quotient of p to the E minus 1 modulo p to the E modulo this previous one? That's of course equal to or isomorphic to the residue field K as an FP vector space, right? All these inclusions here, here it's written p to the I modulo p to the E modulo p to the I plus 1 modulo p to the E. That's obviously isomorphic to p to the I modulo p to the I plus 1, and that we have seen is isomorphic to K as an FP vector space. So the dimension here is F, and there are E terms here. This filtration has length E, and each quotient is of dimension F. So the dimension of O modulo P to the E is EF as claimed. This establishes this claim here. Okay. Now, the third, I'm still proving that the dimension of the ring O as a ZP module is E times F. I've proved that the dimension of the ring O modulo the ideal generated by the number P is E times F as a vector space over the field FP. Okay, but let's come back to the ring, and I take an FP basis of O modulo P to the O. And in the ring O, I take a system of representatives of that base, of that FP basis, and I call that system B. So B is just a subset of O, which when reduced, whose reduction gives me a bijection with an FP basis of O modulo P to the O modulo PO, which I have chosen in advance. Okay, so the claim is that if B is such a system of representatives, then it is actually a ZP basis of O. And of course, the cardinality of B is EF because it's in bijection with an FP basis of this, which we have just shown is of dimension EF. So this is the final thing for proving the proposition. Okay. So in order to show that this is, what do I have to, oh, sorry, wait a moment. Yeah, I have to show that B is a ZP basis of O. So in order to show that it's a basis, I have to show two things, right? That it's a free subset. That's the first thing. Free subsets are also sometimes called linearly independent subsets. So it's a free subset. That's one thing I have to prove. And it's free because its image modulo P is free. I mean, if there was some relation of linear dependence, then I'll get the same relation modulo this ideal. So therefore it's a free subset. And next I want to show that it generates the ring O. Okay. So how do I show that it generates O? Let's denote by M the submodule of O generated by this B. But we know that the image of this B modulo this ideal PO generates O modulo PO, which can be translated as saying that O, although it might not be equal to M, we don't know, we want to prove that it's equal to M, but what we know is that it's equal to M plus PO. It's generated by M union PO. Because modulo PO, the image of B generates the quotient O modulo PO. Okay. So that O is equal to M plus PO is another way of saying it. Now let's substitute for this O, this whole identity for O. So this M, it becomes M plus P times M plus PO. So, and I can rewrite that as M plus P squared O. Right? I mean, you would say that I should write it as M plus P squared O. But PM is contained in M. So M plus PM is actually equal to M. So I'm just writing it as M plus P squared. So if I continue like this, I'll get O equal to M plus P to the N O for every N. Okay. Fine. Then, so O equals M plus P to the N O means that the map from M modulo P to the N M to O modulo P to the N O is surjective for every N. So in the projective limit, the map from M to O, which is just the inclusion of M in O, is surjective. And that's what was to be proved. But one needs to check that this M is actually the projective limit of M modulo P to the N M, the projective limit over little n. And that is true. This is true because M is a free ZP module of finite rank. Right? It's a submodule of the module O, which we already. No, not as a submodule of the module O, but by definition of M as being generated by a free subset. It's the module generated by the subset B, which is a free subset. So it's a free module of finite rank, and therefore it's a inverse limit of M modulo P to the N M. Okay. Fine. So one of the corollaries is, it's a little bit difficult to read this, but it doesn't say anything very deep. It says that if I take a basis, FP basis of little k, the residue field, and if I choose a uniformizer of capital K, then these elements Bi pi bar to the j will form, so forget about these, just read the last line. It says that omega Bi, these are the Teichmüller representatives of Bi, times pi to the j, pi is the uniformizer, and j just goes from 0 up to e minus 1. 0, 1 up to e minus 1. And I goes, of course, from 1 up to f. That is a basis of little k. So these elements, E times F elements, F here and 0 to E minus 1, that's E elements. So this is a sort of matrix having E times F elements, and these EF elements form a ZP basis of O. Okay. So the corollary is that K contains QP. That's because O contains ZP. And the dimension of, or the rank, or it's actually called the degree of K over QP is equal to E times F. That follows from, okay, so since O contains ZP, K contains its field of fractions, QP. And if I take any ZP basis of O, then it continues to be a QP basis of K, and that's why the degree of K over QP is equal to E times F. Okay. So here's the appropriate time to pause for a few more minutes to see if anybody has any questions. Okay. So now I come to a slightly different thing. I now want to determine the structure of K star. K is the P field, capital K. I want to determine the structure of K star modulo pth powers. Now we have already done it in one case. We have seen that if the P field K has characteristic P, then it's actually the field of formal power series with coefficients in the residue field. And in that case, we have determined the structure of the group K star modulo K star to the power P with its filtration. That's what we did a couple of lectures before the present one. So today, we are going to do what happens when the characteristic of the P field is equal to 0. So here goes. We are still assuming that the characteristic of the P field K is 0, and we define this lambda n as being the infimum, or the, whichever is smaller. So lambda n is equal to Pn if Pn is smaller than n plus e, and lambda n is equal to n plus e if n plus e is smaller than Pn. Okay, so that defines a function lambda from strictly positive integers to themselves. And I just denote E1 by E1, this fraction E modulo P minus 1, just to save space. Okay. So this is just a rational number. It's not necessarily an integer, right? It may be an integer, but not always. So what we'll prove is, so we have to study this map, x going to x to the power P in O star, and in what it does to the filtration. The filtration of O star by these are not powers, by U1, U2, UN, where UN is what? Recall that UN, I'm sorry, I can't write now, or maybe can I do it now here? Let me see if I can stop this share and share it from here. Okay. Okay, so it seems to be working again. Okay, so this is where we were, right? E1 is this rational number E modulo E over P minus 1. And I was trying to recall that this UN is the kernel of the map from the ring, or the group actually, O star to O modulo P to the N star, right? That was what the group UN is. So we are going to prove that this map raising to the power P takes UN into U lambda N. Lambda N is here, right? And it takes UN plus 1 into U lambda N plus 1. So if it does these two things, then it induces this map from UN modulo UN plus 1 to U lambda N modulo U lambda N plus 1. And the claim is that this is an isomorphism in all cases, except when N is equal to E1. E1 is this one here, except when N is equal to E1 and K has a primitive pth root of 1. So except in this case, this map rho N is always an isomorphism. That's what we want to prove today. Prove next. And what happens when N is, this was the exceptional case. Huh? The exceptional case means that E1 is an integer and K contains a primitive pth root of unity. So I'll just denote it by this. Okay. So that was the exceptional case. And in this case, the map rho E1 will have a kernel and a co-kernel, which will both be groups of order P. That's what we are going to prove now. Okay, so one of the first thing to prove is these two assertions. You see, that was the first thing, right? This map x going to x to the power P takes UN into U lambda N and UN plus 1 into U lambda N plus 1. So that's what I've rewritten here. This and this. So let's look at what these maps do to an element x in UN. If I choose a uniformizer of pi, this x can be written as 1 plus a times pi to the n, where a is some element of the ring O, right? That's how UN is defined. I mean, UN was the UN. Okay, another way of saying what UN is just 1 plus p to the n. Huh? This is the every element of U. I mean, okay, you understand what this means. Every element of UN is of the type 1 plus an element of the nth power of the ideal P. So if I take some x in UN, x to the power P is going to be this. Now let's expand this. This is by the binomial theorem, you're going to get 1 plus P times this thing here, a pi to the n. And this is the last term. I've written it here for some reason. And these are the remaining middle terms of the binomial expansion. Okay, now let me look at this term PA pi to the n. What is the power of the maximal ideal to which P belongs? It belongs to P to the eth power. That's the definition of E. And what is the power of the maximal ideal to which pi to the n belongs? of course it belongs to p to the nth power. So this product here belongs to this thing here. And similarly, this here belongs to this power of the maximal ideal. So now this lambda n is such that it is equal to the smaller of these two. Lambda n is equal to the infimum of n plus e pn, right? And therefore, these two elements which belong, one belongs to this and the other belongs to this, both of them belong to this here. Okay, that's one thing. Now let's look at these remaining terms. If p equal to 2, then there are no remaining terms. I mean, when you a plus b squared, it just has 3 terms, right? So the proof is over in this case. I wanted to show that x to the power p belongs to p to the lambda n. So if p is equal to 2, the proof is over. What was this? What happened? Yeah. Now, if p is different from 2, we claim that these remaining terms, they belong to this. That's clear because the valuation of this is e, right? Why is that equal to e? That's because this binomial coefficient pi is congruent to, is divisible by p for any I which is strictly between 0 and p. Okay, so the valuation of this binomial coefficient is equal to e. The valuation of this is equal to in, right? Because the valuation of pi is equal to 1. So this whole thing, each of the terms here belongs to the power in plus e of the maximal ideal. But our in plus e is obviously is strictly greater than n plus e, which is greater than n lambda n. So there's no problem. These terms also belong to the power lambda n. So we have proved our statement that we have proved this proposition. And in fact, as a corollary, if you look carefully at the proof, then what is being proved is that if I choose a uniformizer pi of k, and if I write minus pi as epsilon times pi to the e, right? Then, so in fact, this requires this proposition requires a little bit of notation. So all the way here, is just notation. And the assertion, the actual proposition is just this here. So what is the notation? You write minus p as epsilon times pi to the e. Define Hn as the endomorphism. I mean, it's a linear map, right? Which takes a to the pth power, or minus epsilon bar times a. It's just multiplication by this element, or sort of the difference of these two things, depending upon whether n is strictly less than 1, strictly less than e1, or equal to e1, or strictly greater than e1, right? And of course, for every n, we have this bijection from un modulo un plus 1 to k. Let's call it iota n. And the explicit, it's this bijection, right? The image of 1 plus alpha pi to the n bar is alpha bar. Okay, so the assumption is, in that case, the map induced by raised to the power p from un modulo un plus 1 to u lambda n modulo u lambda n plus 1, this is the map induced by raising to the power p. And these vertical maps are the isomorphisms with the residue field k in both cases. And the horizontal map here is Hn. And the claim is that this diagram commutes. It just means that iota n plus 1 composed with rho n is equal to Hn composed with iota n. That's what, of course, means for this diagram to commute. So that this is nothing but writing this out, just a way of re-expressing this. Okay. So this is going to be important. I mean, okay. Now the next claim is that the map rho n, and the same map which I've been discussing, rho n, which is a map from un modulo u n plus 1 to u lambda n modulo u lambda n plus 1. This is an isomorphism for all n, except when this E1 happens to be n equals E1, which means in particular that E1 happens to be an integer. And epsilon bar is a p minus 1th power in the residue field k. Of course, this epsilon was defined as p equals, or rather minus p equals epsilon times pi to the e. That's how epsilon was defined. Okay, so in order to prove this, we just need to prove this corresponding statement for Hn, because what we have is, I mean, we want to prove something about this map rho n, but on the left we have a bijection iota n, on the right also we have a bijection iota n plus 1, and the diagram commutes when I put Hn here. So anything that you want to prove about rho n can be proved by showing the corresponding thing for Hn. So in other words, I want to prove that Hn is an isomorphism if either n is strictly less than E1 or is strictly greater than E1. And then we'll come to what happens when n is equal to E1, etc. So let's first see what happens when n is strictly less than E1. Then the map Hn is just a goes to a to the power p. And there is, of course, an isomorphism, right? It's sometimes called the Frobenius, this isomorphism. Or when n is strictly greater than E1, it's a map a going to minus epsilon bar times a. Now multiplication by a non-zero constant is, of course, an isomorphism or an automorphism in a vector space. So if n is strictly less than E1 or strictly greater than E1, we are done. Let's look at what happens when n is equal to E1. Now suppose that n is equal to E1 and that Hn is not injective. So if it's not an isomorphism, if n, so let's look at what happens if Hn is not injective. That means that there's an a such that a to the power p minus epsilon bar of a is equal to 0. Because Hn in this case is, Hn of a is a to the power p minus epsilon bar times a, right? H of E1, I should say, when n is equal to E1. That's what it was, right? Hn is equal to E1, yeah. Okay, so if Hn is not injective, then there's an a such that this happens. So epsilon bar, now I can cancel a, and epsilon bar is going to be a to the power p minus 1, and therefore epsilon bar is going to be is a p minus 1th power in k star. So what have I proved? If n is equal to E1 and Hn is not injective, then epsilon bar is a p minus 1th power. Conversely, if epsilon bar is a p minus 1th power in k star, then let's look at b to the power p minus epsilon bar b it should be. And this is equal to 0 by definition if epsilon bar is b to the power p minus 1, right? So He1 is not going to be injective. And in this case, the kernel is the set of roots of this polynomial of degree p. So there are exactly p elements. I mean, there could be no roots, but it has the root 0. So it has at least one root. And the point is the kernel of something. So, wait a moment. No, not the root 0. That's not what I want to say. Where is it gone? Yeah, I didn't want to say the root 0. I wanted to say the root b. It has at least one non-zero root, and the kernel has to be a subspace. So if it has a non-zero vector, then it has at least p elements, right? And it cannot have more than p elements because they are all roots of this polynomial of degree p. So the kernel has p elements, and therefore the co-kernel also has order p, because it's a map. H of E1 is a map from k to k. So if the kernel is of dimension 1, then the co-kernel will also be of dimension 1, right? Okay. So the next claim is that for every n strictly greater than E1, the map un to un plus e, n plus e is equal to lambda n, of course, if this n is strictly greater than E1, right? That's why I've written n plus e. You could have written lambda n, but lambda n is n plus e in this case. So the claim is that this is an isomorphism. So how do I prove this? So I take a uniformizer, I write minus p as epsilon times pi to the e, and I take an element y in un plus e. I write it as 1 plus b times pi n plus e, where b is in O. So I have taken an element y here. And I'm looking for an element x. I'm looking for an element x here, such that x to the power p is equal to y. This is what I want to. Yeah, I'm looking for an x in un. So if x is in un, I write x as 1 plus a to the power pi to the n. And the equation I have is x to the power p equals y, which in terms of a and b, what does it become? It becomes 1 plus b. This is y, and this is x to the power p. So you expanded it, you get these terms. And the valuation of this is e, the valuation of this is n. So the valuation of this term here is n plus e. And you can check that the valuation of all these things is n plus e plus 1, because n is strictly greater than e1. So this equation can be rewritten as B equals minus epsilon times A plus pi times phi of A for some polynomial phi in O of t. Okay, so this is what I've rewritten the equation as. Now I reduce this equation modulo. So this is a polynomial, and I reduce it modulo pi, or right? Then I'll get B bar equals minus epsilon bar times A bar. Remember, B is given to me. And this epsilon, of course, is a constant. I mean, it's, and this A is the unknown. Now, this constant, non-zero constant. Now, this unknown, of course, there's a unique solution for the unknown, because this thing is non-zero. You just divide by this on the other side, on both sides. Okay, and so it has a unique root, which is simple, and therefore by Hensel's lemma, there's a unique x which satisfies this equation. Okay, so it's a bit of a clever use of Hensel's lemma, but there's nothing more profound than that. So the next claim is that these UIs are ZP modules. Remember, we had O is a ZP module, but that tells you something about the additive group of this ring. Now these UIs are not subgroups of the additive group. I mean, they are subgroups of the multiplicative group, and I'm claiming that these are also ZP modules. Remember, when k was equal to little k par series t, then we had ui, and we had made them into, or u1 at least, we had made it into a ZP module. Okay, so here's the general situation. We are not general, but it's a characteristic zero case of this thing which we had done earlier. That's a hypothesis characteristic k equals 0 under which we are working. And we are saying that ui are ZP modules even in this case. Why is that? Because each ui is the inverse limit over n of ui of these things, right? I mean, there's an inverse system which you can write down, which is u modulo ui modulo u, what is it? Lambda I and then this is ui modulo u lambda squared I, and so on. So there's this inverse system here, and ui is the inverse limit. But in this inverse system, when I have the term corresponding to n plus 1, it is exponent n plus 1. So it is, this group has exponent n plus 1. Because basically everything follows from the fact that the raising to the power p map takes ui into u lambda I. So if raising to p square will take ui into u to the lambda squared I, and so on. So this thing here is a z mod p to the n plus 1 z module. This thing here is a z modulo p to the n z module. And therefore, in the inverse limit, you will get a ZP module. Okay. So here is the next important thing. For each n strictly greater than E1, the ZP module UN is free of rank EF. Remember, this EF was equal to the rank of the additive group O as a ZP module. Okay, so one of the things, so first I prove that UN has no torsion, because, I mean, if it has torsion, it can only have P torsion. We are over ZP, right? So the only everything which is not in the maximal ideal is invertible. So it cannot have torsion other than P torsion. So UN has no torsion because raised to the power P is a bijection of UN with UN plus E. That's what we have proved above. So if there were to be torsion, this map would have some kernel, and it doesn't have any kernel because these are all isomorphisms. So there's no torsion. So in order to find out what its dimension or rank is, I just need to find the dimension of UN modulo UN to the power P as an FP space. And UN to the power P is the same as UN plus E when this N is strictly greater than E1, right? Okay, so to find this dimension, I use this fact that UN to the power P is equal to UN plus E. So going modulo UN plus E, I get a filtration where you have UN here, UN plus 1 here, UN plus E minus 1 here, UN plus E here. So here you'll just get 0. Here the quotient is K. Here also the quotient is K. So these are all of dimension F over FP. And there are E terms. So the dimension or the rank of UN over ZP. So the rank over ZP of UN is E times F. Okay, so finally, for U1, I want to prove that it's finally generated of rank EF. Why is it finally generated? Because I take any n which is strictly greater than E1, then I know that UN is not just finally generated, but it's also free of rank EF. And it's contained in U1. And the quotient U1 modulo UN is finite, right? Because again, by the filtration, you know that it's finite. So if U1 is if there's a module which has a submodule which is finitely generated, and the quotient is also finitely generated, then of course the module itself is finitely generated. And what is the rank? I mean, if the rank, you just need to look at, if you know that there's a submodule which is of finite index and which is of rank EF, then that's going to be the rank of U1 as well. And that's the case as soon as N is strictly greater than E1. Okay. So let us denote by UN bar the image of UN, image of, what is this? Of UN in this, right? That's UN bar. So you have a filtration of U1 bar. U1 bar is, of course, U1 modulo U1 to the power P, but it has a subspace which is U2 modulo the intersection of U2 with U1 to the power P, and so on, right? So the first claim is that if N is strictly greater than P times E1, then UN bar is trivial. So this filtration is finite, actually. I mean, UN is trivial if N is strictly greater than P UN bar. Huh? If N is strictly greater than P E1. That's the claim, and that's what we are going to prove now. So E1 was this. N is strictly greater than E1, P E1, that's the hypothesis that implies that N minus E is strictly greater than E1. So when I raise the p to the power map on un minus 1 e is actually going to be a bijection with un. That's what we have proved just now, right? So un is therefore going to be contained in u1 to the power p, and therefore its image modulo u1 to the power p is obviously trivial, right? So that's it. There's nothing more to prove. Okay, now the next thing is that if e1 is an integer, then upe1, I mean, this is what we have proved just now. upe1 plus 1 is contained in u1 to the power p. So when I intersect this with upe1, then I'll get these inclusions, right? upe1 intersection upe1, upe1 plus 1 intersected with upe1, which is of course upe1 plus 1, is contained in u1 to the power p intersected with upe1, which is contained in upe1. Okay, so the quotient here is upe1 bar, and so in other words, this inclusion of these three groups gives me a map like this. And the claim is that if e1 is an integer, then this sequence is exact. What is this map here? This is the map which I've just defined. Okay. This is what I've just defined. So the claim is that this is exact. What is the image of this raised to power p map? By definition, it's this. And what's the kernel of this map? By definition, it's this, right? And I have to prove that these two things are equal in order to show that it's exact here. Now, in order to show that these two things are equal, I mean, it's enough to show that e1 to the power p is equal to u1 to the power p intersected with upe1. That's enough. And this is what we are going to show. Okay, so it's enough to show this. So one of the inclusions is clear. This inclusion is clear because, of course, this is contained in this, and this is also contained in this because lambda e1 is equal to pe1. That's how this that's how things are. If e1 is an integer, right? If e1 is an integer, and otherwise lambda of e1 doesn't even make sense because lambda is defined only for integers. Anyway, so this inclusion is clear. Conversely, let's take x in ur, which is not in ur plus 1, for some r strictly less than e1. So I'm now trying to prove the converse here, the inclusion in the other, no, wait a minute, inclusion here in the other sense. This is clear, this what he, okay, so I'm taking an element in some ur, which is not in ur plus 1, then x to the power p is going to be in upr, but not in pr plus 1. But pr plus 1 is strictly less than pe1 when e1 is equal to e model e by p minus 1. Or so you just have to keep using these numerical properties of these numbers to conclude that this sequence is exact. Okay. So I have only 1 minute to go through this. Oh goodness. So maybe there's not, what do I do? So I'll just stop at the corollary. Or maybe if you allow me, I'll just take a few more minutes because next time I want to start a new topic. Okay, so I'll take maybe 5 minutes extra. So now continue to suppose that E1 is an integer, and if this is a pth power, then this is order p, and this is not a p minus 1th power. Huh? This epsilon bar is not a p minus 1th power in k star, then this is order 1. Okay, why does that follow? Okay, so yeah. So that's something that we had proved about earlier, about epsilon 1 bar when it is a p minus 1th power, what happens, and what happens when it's not a p minus 1th power, and so on. Where is it? Yeah. Yeah, so, well. Yeah, here it is, right? So this condition about epsilon bar is what is showing up here. Okay, so actually I can go through the rest of the thing rather quickly because this is very similar to the case k equals, no, not k, it's capital K equals k bar series t. So in this case, we had determined the structure of k star modulo k star to the power p, right? And now what we are supposing is that the characteristic of k is equal to 0 and not p in this case. Here, the characteristic of capital K is p. Now we are in characteristic 0, but things are similar. So the first assertion is that for n strictly less than pe1, the quotient un bar modulo un plus 1 bar is trivial if n is congruent to 0 mod p, meaning it's divisible by p, and it's un modulo un plus 1 if n is prime to p. Okay, so just first consider the case when n is a multiple of p. In this case, we have seen that ups intersection u1 to the power p is us to the power p. And ups plus 1 intersected with u1 to the power p is us plus 1 to the power p. So you write this usual diagram, which we had written even on the previous occasion when we were looking at this case. You write the exact same diagram, and the snake lemma will imply what you are claiming. Similarly, when n is prime to p, so there's some remainder g which is between 1 and p minus 1, then un intersected with u1 to the power p is us plus 1 to the power p, and un plus 1 intersected with u1 to the power p is also equal to us plus 1 to the power p. So you have these inclusions, and these induce this short exact sequence which was being claimed. Okay, so let me just summarize. I have not taken 5 minutes, I have 1 minute left. I'll summarize that the structure of U1 bar, the filtration can be summarized like this. It contains U1, U2 bar, and the quotient U1 bar modulo U1, U2 bar is really the same as U1 modulo U2. And so on, it continues all the time till you reach a multiple of P, in which case UPS bar is the same as UPS plus 1 bar. And of course, UP is not the same as UP, or PS is not the same as UPS plus 1. Huh? Here the quotient is K. Okay, when E1 is an integer and this is a P minus 1th power, then the sequence ends like this. You have UPE1 minus 1 bar, which contains UPE1 bar, and that thing, that group, is cyclic of order P. And the next one is trivial. And otherwise means that epsilon bar does not belong to K star to the power minus P minus 1. K star to the power P minus 1. Otherwise, it ends earlier. It ends at UR bar. UR plus 1 bar is trivial, where R is the largest integer strictly less than PE1. So when epsilon bar was in K star to the power P minus 1, it ended at PE1. Here it ends at the index R, which is the largest integer, strictly less than PE1. So you look at, you go through this again. You ask me questions by email if you have any. And next time we will start a sort of new topic, which is valuation theory, and we will. So the idea is going to be, so basically what we have proved is that K is a P field, implies that K is either a finite extension of QP or K is equal to little k power series T. So next time what we are going to prove is that if you have a P field K, and if you take a finite extension L, what can you say about this finite extension L? Anyway, we are going to start the theory of valuations. So whatever we have done till now is not going to be used, and we are going to start a new topic. So I'll stop there today, right?